Hi everybody. So today I'd like to continue talking about graph theory from last time. We're going to talk about finish our discussion of Euler paths. That we talked about Euler circuits yesterday, but we'll talk about what we call Euler paths today. And I want to talk about something called planarity as well. Planar graphs, as we call them. So those will be our two topics for today, and I think they should be really interesting and enlightening on what graph theory really is. Sure, I'm talking more about specific topics in graph theory, but you have to start somewhere when you're trying to explain an overview of an entire theory. I think that starting with examples and specific points of that theory is can be really nice. So today I'm going to talk about a few things that I find really fascinating, and we'll go from there. So today, planar graphs and Euler paths. All right. So the planar graphs bit will be coming from my own head. The Euler path stuff comes from your book, so or most of it at least. Remember last time I was kind of excited. I found a flaw in your textbook, so I'm thinking about sending a note to the publisher. I don't know what you do when you find flaws in textbooks, but their algorithm, if you remember, for computing for finding an Euler circuit was flawed. So I'll remind you what was going on there at the end of the lecture. So last time I defined a graph in a very abstract sense, but I want to start talking about graphs as in their pictorial sense. So I'm going to be more specific about them. Last time we defined graphs in a very abstract way, as a set known as a vertex set and some collection of pairs. Not necessarily ordered pairs, just any collection of pairs of objects from that set. So that was our definition from last time. Today I want to be a bit more specific. Today I will be more specific about what I mean by a graph. Okay, so that definition, I mean the original definition is the true definition of a graph, but here I'm gonna say a graph is a pair graph is a pair G equals V comma E, where these are capital letters, so they represent sets. Where V is a set of vertices or points, aka these are also known as nodes, depends on who you ask. Vertices or points, but you can really just think about them as exactly that, points in some space. They don't necessarily have to live on an XY axis. We can just look at them abstractly as just points in space drawn on paper, and we don't worry about what the dimension is all the time. Good. So V is a set of vertices or points, aka nodes, which I'll do this in aka nodes which do not lie on an XY plane. I'll write that after. And so a graph is a pair of vertices and edges which basically connect the dots. And E is a set of edges which link two vertices. Like connect the dots. This is how I think about it. And so now I'll write that little remark. The vertices need not lie in an XY plane. That's just to say that we can draw them however we want. So I'll give you a couple examples of these. So, examples. Here's an example. I'll call it G0. It's just going to be a point. Okay. So why is this a graph? Well, it is a collection of vertices. It's a collection of vertices. I mean, it's a collection of one vertex, namely this one. And it's a collection of edges. I mean, that's just the empty collection. We can talk about, like, the empty set was a set. You remember when we talked about sets of objects back in the weighted voting systems? Yeah, we talked about the empty set as a set. So here, V has only one vertex in it, and E has no edges. We wrote that E is the empty set. Good. So there's one. So what I'm going to do is I'm going to do a kind of process here where I'm going to keep on building other graphs by doubling our former graph and connecting all of the dots with edges. So if I do the next one, G1, I can double the dots, 1, 2. So I double it and I connect it with an edge. Okay? So this is also a graph. It's here we double the vertex of G0 and connect the two with an edge. This is how I think about it. And doing something specific. So maybe take a look at our little subscripts here. What's our 0? What's our 1? What are these things going to be representing if I continue this process? So continuing on, I'll do G2. And maybe so now I'll double this one. So I'll make a copy of it. Yep. Good. And now what I'm going to do is I'm going to connect. I'm going to connect the vertices that got copied. So I'm going to connect this one, and I'm going to connect this one. Okay? So again, double or clone G1 and connect each vertex of G1 to its cloned vertex. Okay? Yeah, I won't abbreviate that. Vertex. So in this sense, we had V here, and we cloned it. V hat, clone of V, and then we connect V and V hat, and we connect U, maybe this one's U, and we clone it, and we get U hat over here. And so we'll do it like that. So at each step we clone and then we connect the cloned vertices. Okay, so I wonder if you can see what G3 is going to look like. So we have a pattern going here a little bit. Maybe I'll draw out G3 for you here. So G3, what are we going to do? Oop, I don't know why that just disappears. G3. So I'm going to do a square, just like G2. And then I'm going to clone that square. I'm going to draw it up here. Maybe your doodling tendencies are striking up now. So if I clone the square and I put it there, and now here I have, maybe I'll call this 1, 2, 3, and 4, and when I clone them, I get 1 hat, 2 hat, 3 hat, and 4 hat. Okay, so now I connect all of the vertices with their cloned ones. Alright, that one goes to there. That one goes to there. That one goes to there. And that one goes to there. Alright. And now look what we've got. This is what lots of you might call a cube, right? If we had it if it was a little bit shorter, I mean, maybe you'd call it a rectangular prism. But in fact, what we've done is we've developed the 3-dimensional cube by making copies of the 2-dimensional cube, which we developed by making copies of the 1-dimensional cube, and which we developed by making copies of the 0-dimensional cube. So this is actually the 0-dimensional cube, and this is what we call the 3-dimensional cube. So we call maybe I should make them, we call these graphs hypercubes. I.e. those graphs formed by duplicating a smaller cube and connecting the edges. what's interesting is that via this process we can draw a picture of what an any-dimensional cube looks like, sort of, in terms of its shadow. So this is quite cool. Notice that G3 here. So all of our graphs had no lines crossing over each other until G3. Now here G3 we have 1, 2, 3, 4, 5, 6, 7, 8 vertices. And yet the lines kind of cross over each other like this. See right there. And that's a point of intersection, and what that means, I mean, it's not necessarily a point. Maybe I'll take that back, that phrasing. But what we call that is a non-planar graph, or a non-plane graph. Planar really means that there's no way that we can rearrange it so that the lines don't cross. Okay. So remember, I'll do a capital letter. That distorting / rearranging a graph does not change its structure. I.e., we can think about it as the same graph. Now, watch what happens when I rearrange our G3 up here. So, what we had was one that looks like this. And that's going to go to here. I'll copy that. So what we had was something that looked like this. Right? With our nodes here, 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 and there. Okay. Now from there, I can rearrange this into, well, another one that you probably have doodled a million times. This is why I like these graphs. I've doodled them so many times before I learned about their structure. So we can do the same thing there. We just draw edges joining those corners. Make our vertices. Now it maybe looks a little bit more like the three-dimensional cube that you've seen before. And from there, we can actually get it so that the lines don't cross over each other at all. How do you see how we could do that? Well, maybe in an art class, you might see something about perspective. And so if we just change the perspective a little bit, we can make that square a bit bigger. Make that square a bit smaller, put it in the middle, and now we can join up all the corners. And make a graph, which is the same three-dimensional hypercube, as we call it, embedded in 2 dimensions, we say. So, I think that's quite cool. So, I will write that here, a planar, this is what we call it, planar being 2-dimensional plane, embedding of the three-dimensional here. Oh boy, this is a planar embedding of the three-dimensional hypercube. Okay, and so what does this mean? Def. An embedding of a graph in 2 dimensions, i.e. drawn on a paper, an embedding of a graph in 2 dimensions that is drawn on a page is planar if no lines, with no edges, cross over each other. So an example. So these were examples. Example. Is not planar, but is. Okay? Even though these are the same graph. Okay. So we're gonna use this thought. Oh, one more cool comment. So the fact that we can draw the three-dimensional cube on a piece of paper means that in fact we can embed all three-dimensional objects really into a piece of paper. This is a little bit weird. The cube is really the easy example to understand, but what's interesting is now look what happens when we so if we can draw the 3 cube, we can also draw the 4 cube, right? So we can draw the 3-dimensional. So why don't I say this is actually the reason that we can draw. Is actually the reason we can draw a 3 cube and recognize it. We call we may imagine we can imagine this graph. I'm going to copy it this time because it came out so ugly. We can imagine this as a shadow or projection of the cube. So it's quite cool, and one of the really cool things that we find with this is that so we can't then draw the 4-dimensional cube and really understand what the 4-dimensional cube looks like by drawing it on the paper. But what we could do is understand what the 4-dimensional cube looks like by looking at its shadow in three-dimensional space. So that is to say, what about the four-dimensional cube so I should go back to keep it on saying hypercube, because the idea of the hypercube is we don't know what dimension it is yet. Okay. So then I can do the same process. So I just clone the three-dimensional hypercube, clone the 3 cube, and connect corners. Okay, so that's what I'm going to do. So this corner is going to go there. This corner is going to go there. This corner is going to go there. And this one to there. So now I've got the big ones joined up. And now I'll join up the little ones. Shoop. 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 And shoop. Whoa. So I wonder if you can almost kind of see this as a cube inside a cube now. I can if this was in 3 space, we could kind of see it as like a prism, this little inside prism lying not inside this bigger cube, because remember the perspective says that this little square is further away than this big square, but then this one's further away than the big square here, so almost like the little inside prism here, it almost like goes through the outside. What is the inside? What is the outside? This is the weird thing about 4-dimensional space. We cannot draw the 4 cube in 2 dimensions without crossing lines. But we could look at its shadow in 3-dimensional space. So that's all I'm going to say about that for now. I just think that that's such a cool concept, these hypercubes. I really like them. And they come up all the time. You use these like cubes in all different dimensions to solve problems that you never would have dreamed that they would have popped up in. Yeah, just happened to my advisor in our last paper. So, planar graphs pop up in other places. Planar graphs. So I don't know if you've ever heard of what they call the 3 amenities problem, but it's a little game which lots of people, or a little puzzle that lots of people would not even connect to maths, much like the bridges problem wouldn't have been connected with a branch of mathematics back in the 1700s before Euler solved it. So as a side note, Euler did a lot of work on these planar graphs. Same guy who invented the field also did a lot of work on when a graph is planar, when it is not planar, and we have some really incredible theorems proved just in the past couple of decades about these graphs. It's a big thing at the moment. Good. This is a hot topic right now. Okay. So, let's do the 3 amenities problem. It goes like this. The 3 amenities. So the idea is that, suppose we have 3 houses on one side of the street. So I'll draw a little picture here. So let's say here is the street. Okay, so there's a street, and on one side of the street we have 3 houses. I'm going to draw these houses like a graph theorist, but these aren't supposed to be graphs, they're just houses. Okay? And on the other side of the street, we have 3 amenities. Say this amenity, I'll draw them in. This one is, say, like a water source. And maybe I'll say this one is the electricity. And, well, electricity doesn't need to be a circle. It could be a square. I'll do it here. Electricity. Maybe that's just, yeah. And then over here we'll have a gas. Okay? And so here's what we want to do. I don't like that. We want to connect the 3 amenities to all 3 of the houses. So we want to have pipes coming from the water and the gas, and wires, I suppose, from the electricity. And what we want is that those pipes and wires do not cross over each other. Amenities. We want to connect each amenity to each house without having pipes and wires cross over each other. So we want to connect each amenity to each house. Let's say underground. Good. So the question is, can we do it? So, well, let's give it a try. Do it in green here. Why not? Okay, so let's say that we get, I guess the first step is let's just try doing all of the things to the first house. We'll just connect them all under the road normally. And then maybe we'll try doing the second house. To all of the ones that it can go to. Well, the second house can get to gas just going across the street. But now if we want to get to water and electricity, we're going to have to do something funny. So maybe we'll bring him around this side of the street. And we'll get him to the water that way. And then we'll get him to the electricity this way. Okay. So now we get to this last one, and say we want to go down, we'll connect it to the gas, and we'll connect it to the electricity like this. But now we're stuck. Look at this. If we want to get this house to the water, we have to somehow do it without crossing over any of the other lines. But this is the problem here, is that the water facility is now kind of like closed off from the house by all of these other lines, which kind of block it. And so the answer is no. Why don't I do this one in red? See, this one is no good. So the answer is no, which may seem obvious. By just simple trial and error, but was not proven until Euler gave a formula. And I won't get into all of that. The formula is that the number of vertices plus the number minus the number of edges plus the number of faces is equal to 2. So I just won't even get into that. But you can look up. It's literally called Euler's formula if you want to look it up and find out on your own. Okay, so we can generalize this picture into a graph. The 3 amenities problem can be turned into a graph like this. So we're going to just make the houses and amenities our vertices. Houses and amenities. And the wires are going to cross like this. Well, I've already told you that it's impossible to draw this graph without the lines crossing. So maybe you can think back to what I was just talking about and think, oh, that means it's not planar. Also means it represents a thing which lives in some other dimensional space that we can't fully process in 2 dimensions here. So we call this graph K3, 3. The 3 on the bottom, these 2 3s stand for the number of vertices, the number of amenities, 3 amenities, and 3 houses. And the K stands for complete in German, which basically says we draw all of the edges between them. And we have a theorem, so we call this graph K3, 3. What other non-planar graphs exist? We have a cool theorem by Robertson and Seymour, which was proved about 15, 16 years ago. A cool theorem by Robertson and Seymour in 2004 says that, so proved by Robertson and says that every non-planar graph, that is a graph which can't be drawn without lines crossing, contains either K3 or K5 inside it. Okay, so a K5, I'm going to say, so K3 is what we saw above, and a K5 looks like this. It's 5 vertices, and all of them are connected. So oop, it did not like that. I'll just draw it normally. Okay, so this is what a K5 looks like, and it's the other one that we can't. It's another one of the very most basic non-planar graphs. So I'm going to say we can relate this back to our bridge problem. So here's how. Suppose there is a city, much like Königsberg, laid out like this. So what we're gonna do, we're gonna have, I want to have the northern part of the city divided by a little river, which comes down and meets the big river down there. And so I want, and then I want to have one island there and one island there. And this is all water. Okay? So your city is now divided into 5 parts. Is divided into 5 parts by water. They want to an architect would like to design bridges. How many bridges? Well, would like to design bridges which connect every landmass sorry, just English, like trying to figure out how to phrase this. Connect every landmass to every other landmass without crossing. Bridges. And so now the question is this possible? So, well, let's give it a go. We could make a bridge here, and 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 those aren't going to cross over each other. So now this landmass is connected to every other landmass. Okay, so now we can do this bridge up here to connect those two. We can do this bridge down here to connect those two, and this bridge over here to connect those two. We can do a bridge on either side connecting those two bits and those two bits. So now those are connected. So first of all, how many bridges am I supposed to have? Recall, we know how to calculate the number of bridges needed. This is the number of ways to make pairs. Remember, our edges are just pairs from our vertex set. So this is just the number. This is simply the number of ways to make pairs. Distinct pairs. Of 5 things. And so this was, so the number of pairs is, remember we had 5 choices for the first coordinate times 4 choices for the second coordinate, but then we count every one of them twice because we flip it. So we divide by 2, and that makes 10. So we're looking for 10 bridges. And now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the bridge that we're missing? Well, none of them cross over so far we're good. But the last thing that we'll have to do is connect. Well, this one has 4 coming out of it. This one has 4 coming out. We have to connect this one to this one. But look at this. If we try and go through just like that, now these bridges cross. That's no good. So we don't want to do that. Is there any way that we could do it? No, we don't want to cross over land because this is kind of like too big. It's cheating. So, well, why don't I just say, unless we can cross over land, then we're good. But if I add the assumption that our bridges can't cross over, then it doesn't work. So that's a no good bridge. And when we draw this in graph form, it becomes more clear. In graph form, we have 5 vertices. So we can draw those out just like they were in our land masses. So remember we had 2 land masses up there, and then 2 islands in the river, and then 1 land mass down there. And now we want to see if we can connect all of those with edges representing bridges. And we're good. We can do the cycle around the outside, so we can make a cycle of them. And then we can connect those 2 like that. That's alright. Now we want to connect this one, but now we crossed there, so we can't do that. So we'll go around the outside like this. And then likewise, we want to connect this one to this one, so we've got to go around the outside again, because we can't go through the inside. And now we're stuck on this vertex, right? Because these two have to join, but we can't go through the inside, and we can't go through the outside without crossing over a line. So that's the idea, is that this edge is a bad edge. Nowhere we can put this edge without crossing lines. Okay, so that's my spiel on planarity. Good. The next bit I'll do is on finishing up Euler paths, but I'll stop this video and make a new one there.